Welcome to this video lecture. Myself Atul Kumar, working as a assistant professor in Department of Computer Science, Rajiv Gandhi Memorial, Government College, Jogindanagar. In this video lecture, I will discuss about timing and control. So, what are clock pulses? The timing for all registers in the basic computers is controlled by a master clock generator, or a master clock is there to generate or to control the timing of all the registers in the basic computer. So computer pulses are applied to all flip-flops and registers in system, including the flip-flop and the registers in the control unit. The control clock pulses do not change the state of the register unless the register is enabled by the control signal. So firstly, there is a control signal that is generated by the control unit, and after generating the control signal, the clock pulse change its state or change the state of the register. So the control signals are generated in the control unit and provide control inputs to the multiplexers in the common bus, control inputs in the processor registers, and the micro operations for the accumulator. Uh, so the control signals are generated by the control unit, and these control signals are applied to all the multiplexers in the common bus, control inputs in processor registers, and the micro operations for the accumulator. So next is, what is hardwired control? There are two types of control organization in computer architecture. One is hardwired control and other is microprogram control. So as the name suggests, hardwired control is basically made up of or created with the help of a hardware. So in hardwired organization, the control logic is implemented with the help of gates, logic gates, flip-flop, decoders, and other digital circuits. So they have advantages that it can be optimized to produce a fast mode of operations. As we can see with the advancement in the hardware, uh, that with the increase in the number of logic gates, with the increase in number of flip-flops, decoders, we can increase the performance of hardwired control logic. But in case of microprogrammed control, the control information is stored in the control memory. So there is a control memory in case of microprogrammed control, and this information is stored in the control memory. The control memory is programmed to initiate the required sequence of micro operations. So there are micro operations which are initiated with the help of control memory. So control memory is programmed to initiate the required sequence of micro operations. In the microprogrammed control, any required or change or modifications can be done by updating the microprogram in the control memory. So this one is the block diagram for control unit. So you can see here, in the control unit we have a instruction register, we have a decoder. We have a decoder of 3 into 8. Two decoders are there. One is of 3 into 8 size and other is of 4 into 16 size. We have a sequence counter is also there to count the sequence, and we have a control logic gates. So firstly, you know very well that what is the purpose of instruction register. So in case of instruction register, instructions are firstly stored or loaded from the memory to the instruction register, and in here, in case of control unit, the instruction registers is the size of instruction registers is of 15 bits, and out of 15 bits, the first 11 bits are given to control logic gates. So the output of first 11 bits are given to logic gates. The next bits 13, 14, 12, 13 and 14, they are given to decoder for a decoding purpose, and the 15th bit is given to the I register or I register. And here also you can see the output of decoder. And the output of decoder gives 8 output here, as it is a 3 into 8 decoder. So we have 3 inputs and it is decoded, or these 3 inputs are decoded to 8 outputs: 0, 1, 2, 3, 4, 5 and 6. And these output lines D0, D0, D1 and up to D7 are given to control logic gates. Next we have a decoder of 4 into 16. That means it has a input of 4 and output of 16 lines as a output. So in case of sequence counter, it is a 4-bit sequence counter, means it gives you a binary number of 4 bits. So it can produce a binary number from 0 to 15. As to produce a binary number of 15, 4 bits are required. And it has also a clear counter, a clock is there, and increment is also there. So sequence counter is incremented one by one. Firstly it produce a output 0, then 1, then the sequence counter is incremented and it produces a output of 1, then it produces a output of 2 and so on. And these outputs are given to the decoder, and after decoding they produce or they generate 15 outputs from 0 to 15, and to produce a timing signals from T0 to T15. So T0 to T15s are again applied to control logic gates. And so we have D0 to D7 as a output of decoder 3 into 8, and T0 to T15 as a output of decoder 4 into 16, that are applied and as a input to the control logic gates, and it produces a control output, or control signals are generated according to the control inputs that are generated with the help of these decoders and sequence counter. So as we have seen, control unit consists of 2 decoders, a sequence counter and a number of control logic gates. The instruction read from the memory is placed into the instruction register. So instruction registers is divided into 3 parts. The first part is I bit, the second part is operation code, and the bits from 0 to 11. The operation code in bits from 12 to 14 are decoded with the 3 into 8 decoder, as I have discussed earlier. The 8 outputs of the decoder are designated by a symbol D0 to D7. This one is also discussed earlier. Bit 15 of the instruction register is transferred to the flip-flop designated by the symbol I, and bit 0 to 11 are applied to the control logic gates. The 4-bit sequence counter can count in binary from 0 through 15. The output of the counter are decoded into 16 timing signals from T0 to T15. As I have discussed earlier, there is a decoder of 4 into 16. So it has an input of 4 and output provide 16 timing signals from T0 to T15. The sequence counter SC can be incremented or cleared synchronously. Most often the counter is incremented to provide the sequence of timing signals out of 4 into 16 decoder. The sequence counter responds to the positive transition of the clock. So there are two transitions of clock, one is positive and one is negative. The sequence counter always respond to the positive transition of the clock, and this means that sequence counter is active with the positive transition of the clock. Initially the CLR means clear input of the sequence counter. SC means sequence counter is active. The first positive transition of the clock clears SC to 0. Firstly the sequence counter is cleared to 0, which in turns activate the timing signal T0 out of the decoder. So during the first positive transition, uh, during the first positive transition, the sequence counter 0, it produce a 0 and the timing signal T0 is activated. During the second clock pulse, it is incremented to 1 and the timing signal T1 is produced as a output, and so on up to T15. After T15 the clear is activated and the sequence counter again return back to its initial position 0. So the a sequence counter is incremented with every positive uh, clock transition until its CLR input is activated. So the sequence of timing signals T0, T1, T2, T3, T4 up to so on T15 are produced as the positive clock transition activated. uh, so this one is the timing diagram showing the timing relationship of control signals. Thanks for watching this video lecture.